Hello, this is the supervised version of the tractography segmentation. My name is Eleftherios Garyfallidis. I'm a professor at Intelligent System Engineering of Indiana University. And I will show you some tools that we have in Dipy for segmenting and recognizing bundles in large tractograms. Okay, so here we are. To do supervised segmentation, because you need label data, and the label data often come from correlations with anatomy, with anatomical images, you have to have a registration algorithm that you can use. So to accommodate supervised learning, we developed this Streamline-based linear registration algorithm called SLR. And this is a robust and efficient linear registration, so it's an affine registration of white matter fascicles in the space of streamlines. And it's a method that is robust to incomplete data. For example, if you see here, you have two bundles those are singulum bundles from two different people. And those are in the same space now, but they are from different people, so they're not matching exactly. If you use SLR, you can make it match, even though the data are incomplete in a sense that you don't have the same number of streamlines, you don't have the same length of the streamlines in its bundles. You can see this one is turning here a lot, but the red one is kind of, this one is turning up, and the red one is turning down. So how can we put this together? Well, SLR can do it up to whatever the affine transformations allow it to do, but it can do a really good job with incomplete data. Okay, so then here is an example of how this looks like. You have two bundles, and then you register them together, and here is the registration. It started. Here are the number of iterations, and then you will see it rotated to see how good is the overlap. And you can see there is really a lot of overlap, even though the shapes are quite different. Now, we have not warped this bundles. This is just a fine registration. I say just, but actually to solve this registration problem is not trivial to do. Okay, and this is for whole brains. This is before and after registration. The red streamlines belong to a tractogram of one subject, and the greens to another subject. And the way we deal with these large tractograms is, of course, we are running quick bundles first. We simplify the tractograms and then do the next part of the analysis. All right, so if we now move to the next slide, you can see what is the actual objective function, the cost function that we're using. So imagine that here you have two sets of streamlines. Okay, you have two sets of streamlines. Here is one set of streamlines, right? And here is another one. So imagine the rows are capital A and the columns are capital B. So those are the two different sets. So imagine now you start calculating the distances from one streamline from one set to the other streamline to the other set. This is shown here as D. And if you see here, I is enumerating from 1 to A and J from 1 to B here. Okay, here I'm talking about this part. So what we do, we're calculating all the MDF distances from the streamlines of set A to the streamlines of set B. But what we do after that, we don't just use a cost metric that, let's say, it takes an average of all these distances, or it looks only at the diagonal or something like that. But what we do, we keep the minimum value for each row. So we go to this row. Sorry for that. Undo. We calculate the minimum value for each row. For each one of these rows, we calculate the minimum value and keep those. And we do the same as we do the same for the columns too. This is what is shown here in this equation. This creates a very robust metric that then we can use it to do optimizations. And we can say, you know, when this metric will be small, that means that the bundles are matching very well together. If it's not small, that means that the registration needs to continue. So, and this is what it shows here. So we have the moving bundle here as M, and some transformation that then is applied and compared to the static bundle. And we're trying to find the transformation, the set of transformations here that provides the minimum BMD value. So BMD stands for bundle-based minimum distance. And those Ds you see here are actually the MDFs, are the MDF distances, because they're acting on streamlines. Okay, so if you use that objective function, then you have this very nice robustness in finding and matching the bundles and using it for registration. And you can use that, for example, to create atlases of bundles, or you can create atlases of whole brain tractograms. And here you can see, for example, how we're building an atlas of the optic radiation, and we are combining many of those bundles that we register them together. This is the affine version of the SLR. And you create, and we register all those to a reference subject, and then we just count the streamlines to make this atlas probabilistic, and then you can see how impressively sharp is the result. And the probabilistic atlas looks really, really well created, although it has been created completely with streamlines, with streamline-based registration. Okay. So this is an application, and you can use the same method to create different atlases of pathways across species. This is not only for human subjects. All right. So for whole brain linear registration, someone may ask, shouldn't that distance matrix that I saw here in the previous slide, that distance matrix here, shouldn't that be like massive in size? And the answer is yes, it will be massive, but we don't use that. We are calculating that matrix on the centroids of quick bundles, because those are much less. It may be like maximum that matrix may become like 4,000 by 4,000 in size. And then you don't really lose anything, because quick bundles provides a really compact version of the tractogram. So again, quick bundles is saving the day. So let's go now to the next part. So, okay, we have a registration method. It works really well. That's great. But now, how do we go towards the supervised segmentation? First, I should say that for at least 10 years, people have been doing a lot of manual segmentation. So they use some visualization tool, and then they add some planes or regions of interest, and they filter the streamlines. So that's what people have been doing for a long time. And but it's work. It's a lot of manual work, and we want to not have to do that. So to move beyond manual segmentation, apart from needing like a good registration method for tractograms, we also need to have labels, and those labels we could use using manual segmentation. So we will have a training phase, and for the training phase, we will have to have some labeled datasets. Now, I introduced a method that needs very small number of labeled datasets, and that's RecoBundles, recognition of white matter bundles using local and global streamline-based registration and clustering. So that method needs only, for example, let's say you want to recognize or segment the arcade fasciculus. Okay, you need to extract minimum one arcade fasciculus from a healthy subject. And that would be enough to extract from other subjects. So this is called in machine learning one-shot learning. One-shot learning, and the idea is that you learn basically from very few number of examples. So RecoBundles needs you to provide some examples of the bundles you're looking for, only a few, and then it will recover them from other datasets. Look here, we provided this bundle in some old deterministic tracking dataset, and here is what the expert segmented in other datasets. So here is this row is subject 1, subject 2, subject 3, subject 4, and you can see that in all cases our method RecoBundles recognize really well what the expert segmented. All right, so, and that was the model bundle, the same model bundle used for all subjects. That's it. Okay. All right. And now that was in the original paper. In the recent work we have with Brahms, my PhD student Brahms Chandriosi, used a refined and even improved version of RecoBundles that is available in Dipy that does a further refinement on the final extraction. But if you want to see how the method is working, you have a target and a model tractogram. Those are full brain. You register them. Okay, this is SLR so far. And this is where the RecoBundle starts. So now you have these two datasets registered. You provide a model bundle, and then you get an extracted bundle. And then there is a refinement step that can improve further that extracted bundle. So then you have a bundle that is very similar to the model bundle. So if you provided arcade fasciculus, you will get arcade fasciculus back. So, and you can repeat that with many bundles. So then have a series of bundles. And we provide a template as a facilitation so that you don't need to go and extract bundles manually on your own. But be happy also to use Horizon or the other tools we provide to build your own bundles and use those as model bundles to then do recognition. Okay, so one very nice thing with RecoBundles that was shown with the paper is that it works in datasets like this one that have very large tumors. And you can see it here, for example, this is the FA of a subject that has an extended grade 3 glioma tumor. And this is the model. This is the model. And this is the expert segmentation that took hours to make. And this is the automatic segmentation. Okay. This was a very hard manual segmentation because you have the tumor, you have edema, you have to combine many things to be able to find this. You cannot just put one ROI here, you get everything. Because as you can see, many of the streamlines are broken. But the automatic version of our method, RecoBundles, does similar. And if you see also, the result is denser, like it seems it can pick things that the expert couldn't pick. So this gives a lot of hope for clinical data sets. So both the SLR method and RecoBundles are ideal for clinical data sets and will work in cases where image-based approach do not work well because the registrations are failing and so on. So I definitely recommend you to use this method and try them, understand how they work, and of course, ask questions in the Dipy forums and chat rooms, because there is really great potential. And after many years of playing with these things, we have understood that indeed there is a great potential and they can be used for very hard data sets, very hard clinical data sets. Okay. So one of the key concepts of RecoBundles is sparsity. The method takes account in the fact that if you have a data set and then you cluster this data set with quick bundles, then the centroids are a much sparser representation of that data set. So what you can do, you can then use that to reduce the search space, which is shown here. So here in phase A, we reduce the search space. So basically, let's say you have a type of an uncinate bundle shown here with that sketch. That's your model bundle, is an uncinate bundle. What you can do, first phase is use the centroids of this bundle against the centroids of the whole brain tractogram and remove everything that is way too far. So that gives you some kind of neighborhood. And then what you use SLR now, but now locally. SLR, because it's so robust, it can go and find from all these kind of options here the best option. And then that's phase C, where now the model bundle is on top of the target bundle. And then there is a final pruning step in C, which you can see here. There is a final pruning step. So everywhere here, the MDF distances are being used to do this cleaning, the pruning. And we have seen that for a very large type of data set and pathways, the thresholds are the same, especially after also the refined version that is explained in the bundle analytics paper of 2020. This has become clear that you can get with RecoBundles many of the pathways in a very easy and fast way and really accurate, even though you're using very few initial labeled data sets, labeled bundles. Okay. So here is some of the results as well. We saw here that even though we're adding defects in the bundles, that's again for clinical data sets, that the method is robust and the Jacquard indices This is like the dice score, are staying high. Right, so here's the summary of RecoBundles. RecoBundles can be used to test hypotheses of the existence of bundles. So if you find a bundle that you have never seen before in one dataset, you can use RecoBundles to search this, to identify these bundles in other datasets. It can use a single model. There are versions of RecoBundles that use multiple models if you're interested in that. Extract the pathways very accurately. And it was used actually to evaluate the results of the International Tractometer Challenge that provided the Nature Communications paper of 2017 by Mayer and Hain. So in that challenge, we had to use RecoBundles. There was nothing else to use because role-based filtering for such data set that had small deformations and changes, it was very hard. And then the team running the challenge, they couldn't evaluate the results using region-based, image-based filtering of tracks. But RecoBundles was working and was providing the results and helped to evaluate. RecoBundles, remember that too, is also 100% streamline-based. Like it starts, the input is tractograms, okay? And it stays with that. It's adaptive to pathological brains, tumors, big ventricles, and so on. And it's built off top of QuickBundles X and SLR. Okay. So that's the summary of RecoBundles. Now, to use it, you can use Dipy, you can use it with the Dipy API. There are tutorials available for that. But also there are interfaces to facilitate. So you can run first Dipy SLR with the model brain and target brain. That will solve the initial registration. Then when you're that, you select a model bundle. For example, here we have added these model bundles AFL, left arcuate fasciculus, and the target registered brain, which is an output of Dipy SLR. And if you want, you can have the new option to do the refining. And after that, you have the extracted bundles. You get extracted bundles. Here, you will get one bundle because we provide only one. But you could have many. You could have many included here. You could have an asterisk and provide many of those, or provide an atlas. So you will hear from Brahms more about this. And then with label bundles here, what this is doing, this function is providing exactly the same result, but in the original native space, because here you are in a common space. But with this function, you get the result also in native space. All right, so this is how to run RecoBundles. You just need these 3 commands. Of course, if your datasets are already registered in the same space, you start directly from this. You don't need to do the initial step. Okay, so I'm clearing this. And now, another method that is using MDF distances is ClassiFiber. And if you have data sets that are already labeled and you have many labels, many data sets with the bundles labeled, you can use ClassiFiber. And ClassiFiber, what it does, it uses more distances. So for example, it will use the MDF, but also it will use the endpoints, the Euclidean distances of the endpoints. So here we'll use something like the MDF, and here you will use the endpoints, Here you would also use some knowledge we have from anatomy about the ROIs. And then using that, it can represent its streamline as a vector of those distances. And using that, it can run a classifier. That's why it's called classifier. It can run a classifier, and at the end, just with linear regression, they can get high accuracy. But of course, here this method, it requires more data sets to train. But that's another option. You have it. Thank you.